What I'm going to tell you about is an update from basically the report from last year. So what's new in optical astronomy at the South African Astronomical Observatory. So it's not going to be a comprehensive overview, but the new stuff. You will recall that last time I was here, I told you we were bringing in a new 1-meter telescope. The good news is it's here. So it was installed just last month. It's in commissioning now. It's working very nicely, as I'll show you a few pictures and things from it. And so we have sort of test instrumentation on it now. The new instruments are coming. It opens a new field of work for South African astronomy, optical astronomy. Heretofore, all of our telescopes had fairly narrow, in fact, quite narrow fields of view on the sky. This is a wide field telescope. It's got 3/4 of a degree field of view. So it's going to afford many new opportunities, particularly for survey sorts of work that were difficult, if not impossible, to carry out with the older telescopes. And it's going to challenge the South African astronomers to start thinking in different ways of how you use such a wide field capability on this telescope. It will have a wide field camera. We've got a 6K by 6K 36 megapixel CCD in-house. It's being integrated into its doer and the electronics are being worked on. We expect to install it on the telescope later this year. And we have funding for 1, and if we can stretch it, 2 spectrographs, a low resolution and a high resolution spectrograph that will also go on this telescope. So it'll have quite a range of capabilities. It's a cute little telescope, as you can see. Here's Hannah Vorters, who's the PI, the project manager, and has been really the inspiration and the person who's driven this project forward. She's one of the astronomers at SAAO. It's a LDAS mount, as you see, which is also new for SAAO telescopes. All our previous ones were equatorial mounts. Of course, SALT is an LDAzimuth mount as well. That makes it much more compact. It fits easily within what used to be the 3/4 meter dome, and you see it's got room to spare inside the dome that held a previously smaller telescope. It's got 2 focal positions at the so-called Naismith foci. The primary reflects up to the secondary light comes down through this baffle to a 3rd mirror which folds the light off to a focus which goes through the elevation axis, and there's a focal position on each side. This tertiary mirror rotates 180 degrees to feed either one or the other of the 2 foci. And so we'll have the wide field camera on one side, and we'll have the spectrographs and any other instruments we can think of on the other side. So they'll all be on the telescope at the same time. You can rotate back and forth between them quite quickly. So here are just some more pictures. This is looking at it from the other way. Probably not as exciting. Here's looking down on the primary mirror. Those of you with eagle eyes will notice in a month it's also already collected a little Karoo dust on the primary, unfortunately. These ports on the side are the ports going off to the Naismith foci on either side, and there is a hole in the center of the primary, but it's not a Cassegrain, and there's no imaging position behind the mirror. The light gets deflected by the tertiary, which is in this structure, and this is the structure that rotates around 180 degrees to feed the 2 Naismith foci. And then here's a view of that tertiary mirror, also with a little bit of dust on it already, inside this rotating structure. And I'm talking to an amateur group, so I have to show you that there actually is an eyepiece on the telescope right now. We won't be looking through this telescope much, but this is the side that will have the 6K by 6K big CCD on it. So until that arrives, there's an eyepiece installed. This is the auto guider. There's an auto guider on each side of it as well to keep it tracking properly. Lots of nice little engineering in various places. Since it's an LDAS telescope, this whole structure has to be driven to rotate because the image on the sky rotates for LDAS telescopes. That's the difference between this kind of mounting and an equatorial mounting. And every telescope has to have a nameplate, so this one does too. It's built in Germany and actually shows when it was installed. We are about to announce a nationwide competition to name this telescope. We're going to solicit school children across the country to submit names for the telescope. We're in the embarrassing situation that we have 2 1-meter telescopes. I mean, we used to have a 1 meter and a 1.9 meter and SALT, but now we've got the 1 meter and the 1 meter and the 1.9 meter. So we need a new name for this telescope. So we're going to solicit children across the country to submit their names with a few sentences describing why they chose that name. Some few unlucky persons are going to have to look through those thousands of submissions and choose the winning name, and then we're going to bring the school child with their parents to the observatory to have a dedication ceremony where they'll get to cut the ribbon on the telescope and participate in the first night's observing as well. So I can't tell you what the name of this telescope is yet. Maybe next year. We hope to have that naming ceremony probably February or March of next year, sometimes when the weather is nice up in Sutherland. So here's just a movie of it moving, if this works. Let's see if this will run. Yes, it moves very quickly. It's got a very fast drive. So this is real time. You'll see it zip around the sky. This telescope is all under computer control, and it's also got remote and robotic software on it. So part of the installation was to refurbish part of the dome and the observing room and stuff, but we hope most of the time that the observers won't actually be at the telescope. They'll be off back at their home institutions running this remotely over the web. One of the things we had to do was raise the floor because the old large telescope was sitting deeper into the dome, and with the size of the older telescope, it then was up at the right height to look through the dome. This smaller, shorter telescope had to be raised up to look properly through the dome slit. So we raised the floor by about 1.6 meters or so. So I think there's probably more engineering in the floor than there is anywhere else in this telescope. There's pretty hefty structure to raise it up and support the 1,000 kilograms or so of the telescope. And then here's a view. The old pier was cut down and a new concrete structure was poured over top of it to support this telescope. And again, you see now there's a little ladder going up to the new level of the observing floor. And the motor drivers and things are sitting down here. So here's a on-sky image, what we call the first lights image of the telescope of the globular cluster M45. This is a 45 arc minute, 3/4 degree field of view. You're all being very polite. Nobody's saying, why is it off center? This was when they first mounted the camera on the telescope and they didn't quite get it in the right place. So this shows that it really is first light. They are getting it lined up now. This is also this shows, interestingly, the field of view of the telescope. You'll sort of notice there's a checkerboard pattern in there. That's because this is taken with a small CCD camera that was then on a stage that could move it around and take picture after picture after picture. So this is a 8 by 8 mosaic, 64 frames to cover that full field of view. interestingly, the same CCD camera that took each one of these little frames that's in here was able to cover the full field of view of the other older telescopes that this one's replacing. So the older telescopes, you can actually see it maybe a little better over here, had a field of view this big. This guy's got a field of view that big. So it really is going to change some of the things we're able to do. You'll also notice the image quality is excellent over the whole field. We're very happy, and it's basically worked this way out of the box. Didn't need any additional alignment. Some of the manufacturing team came down from Germany to help install, and they really did a superb job on this telescope. Let me go on to talk a little bit about SALT. SALT is in routine science production. It's been so for the last 9 semesters now, 4.5 years. All of the instruments are online, running and producing data every night. Maybe not tonight, it might be a little cloudy up there, but every clear night it's turning out the data. The near-infrared extension of the prime focus spectrograph was now scheduled to arrive in 2019, safely after I'm gone. So somebody else will have to tell you about that. And we shut down last month for a month for routine service. It's like taking your car in for oil change and we're fixing the tires and stuff. And that was very successful, went off on schedule. We did a very large number of things to the telescope, and by cleaning mirrors, cleaning optics, replacing the fluid in the optics, the spectrograph now has 20% greater throughput than it had before the service. So we pay back that 1 month of service in 5 months, and then everything after that is additional throughput, additional efficiency on the telescope that we wouldn't have had. The big new thing this year was last April, the segment alignment system that controls the 91 individual mirrors that make up SALT's primary mirror was installed. Those of you who are into SALT history will remember that the original system was a failure because it relied on capacitive sensing, and the large swings in relative humidity at Sutherland, just the system couldn't cope with that. So we designed a new system based on inductive sensors that's now fully installed and working, and it's working beautifully. It's controlling the mirror so that previously we had to realign the mirror every time the temperature changed by a few degrees. And so on a good night, that meant we'd have to align at the beginning of the night, in the middle of the night. On a bad night, you might have to realign the mirror 4 times because the truss that supports the mirror expands and contracts with temperature and moves all the mirror segments around. So this new system senses that and automatically corrects it and keeps the mirror in good shape. We can now, our record so far is we can run 21 days without realigning the telescope, and that was limited by a power failure, so we don't really know how long we can go without realigning the telescope. So far it's been limited by SCOM, not by the mirror technology. This is an image, this is sort of a historic image, and I was privileged. I took this image, I was observing on the telescope. This was the first night when the primary mirror had not been realigned at the beginning of the night. They carried over the alignment from last night, the previous night, with this control system, and we're obviously getting very good imaging, 1.2 arc-second seeing basically that night. And this telescope is now delivering seeing image quality that's as good as the free air seeing. We measure the free air seeing with a separate monitor outside the dome, so-called dim telescope. And when we measure the images that we get with SALT, it's basically giving us what we would get if we had a perfect telescope looking through the atmosphere. So we're very pleased with this system. It's contributing enormously to the efficiency of the telescope, not only because we don't have to go off and realign several times a night. Each realignment took somewhere between 15 and 30 minutes, but also because with the better image quality, you get more light into the spectrographs, so everything just goes faster. So SALT is working really well, and we're really happy. One of the things that we did this spring was we had a guest instrument from a Scottish university, Heriot-Watt University in Edinburgh, a thing that's called a laser frequency comb. This is a picture of it in operation at the high-resolution spectrograph on SALT. It's very pretty. There's actually a laser that puts out ultraviolet, which you can't see here, and then that's frequency doubled, frequency half, wavelength doubled, up into the green, the visible part of the spectrum. Then that laser then feeds something that either you could say is remarkable or it's black magic, one or the other. It's a photonic crystal that when the light goes into that, it goes in as a single color and it comes out broadened across the entire spectrum. And it puts out, instead of a single line, a single wavelength line, it now puts out a forest of lines, evenly spaced, equally bright, and you know exactly the wavelength of every line. So it's used for calibration, and it gives a much higher precision calibration of this spectrograph, which allows us to get down to meter or perhaps centimeter per second accuracy, which will allow us to start looking for planets with higher precision using the high-resolution spectrograph. This is the first time such a unit's ever been used in the field on a telescope. They've been used in the lab, but actually taking it into the field and getting it working in the telescope environment, this was a real first, and SALT was able to do it. And here's a picture of a spectrum. So the brighter bands are a stellar spectrum. You can see the continuum and the absorption lines, the dark lines caused by elements in the star's atmosphere. And then above each of those orders is a calibration spectrum. The individual bright lines are a thorium-argon source, the calibration system we had previous to this laser frequency comb. And you see there are several, but they're pretty widely spread. There are some places where there are hardly any of those individual calibration lines. So there are some places in the spectrum where your wavelength calibration is uncertain and thus your precision is lower. Also, there are different brightnesses. Some of them are nice and bright and can be measured with high signal noise. Others are quite faint and hard to see and will be lower precision. The forest of lines that you can see, this sort of picket fence of lines, that's the laser frequency comb. So you can see it's putting out a very regular pattern, equal brightness lines, very closely spaced all through the spectrum. So it gives us a tremendously precise calibration of exactly what wavelength is where in our spectra. And that's the advantage of this thing. It was only on loan, it's gone back to Heriot-Watt, but they were so pleased with the results that we're already talking about a second campaign with a new generation instrument that will apply some of the lessons learned from this 3-month campaign that we had at the beginning of this year. And just for a pretty picture, this was done last week. This is a nearby galaxy in G613. A supernova went off certainly within 24 hours, probably within about 12 hours. SALT was able to get on it, and this is the supernova, a single star that's exploded in this other galaxy, putting out amount of light comparable to most of the 1,000 billion stars in that galaxy. These are the things that are so bright they can be seen on the other side of the universe, and there are our yardsticks, our meter sticks, I'm going to convert to South African here, for measuring the distance scale of the universe. So this is very nearby, but we want to understand these things in as much detail as we can so that when we see one billions of light years away, we can relate it to the ones we see nearby and understand in detail the processes and give our measurements just that much more accuracy. So it's important to look at the nearby bright ones in great detail, and that's what SALT did with this image. I was at a NRF meeting last week, and I showed this because it had been done just the night before, and they produced this picture in a few hours and sent it through to me, and I flashed it up on the screen, and I said, real-time, almost near real-time results from SALT. And they said, well, how far away is that? And I said, oh, I don't know, I haven't looked it up, but it's a few megaparsecs, so that means it's 10 million light years away, so what you're seeing is happened 10 million years ago, they all said, 10 million years ago. And I said, yeah, but we can see these things billions of light years away. Back to the beginning of time. Okay, well, that's not all that's going on at Sutherland. Since I'm here at SANSA, I have to give credit where credit's due. We are now hosting some facilities from the Space Agency on the mountain, and this is the first one that's installed in this trailer. It's running now. I think Mike will tell us more about what's going on. I'm taken by the little hemispherical domes on top to look through. They are clear, so you don't have to move them around and stuff. I'm betraying my age, but some of you are my age, so you will recognize this as well. That struck me looking at that. I said, I've seen something like that before. So the Jetsons' car had one of these hemispherical domes on it as well. In addition to the astronomical stuff, we have addressed a problem at the observatory. We've never had very satisfactory emergency medical evacuation facilities. If somebody gets hurt at night at one of the telescopes, we've had contracts with a number of companies in South Africa. They've all proved unsatisfactory. So we finally, between the SALT Telescope Consortium and the NRF, funded our own ambulance. And so we converted one of our vehicles into an ambulance. We're training the staff up. One of our staff members already has basic ambulance training certification. We're training other members up to that same level. And so we will now be able to evacuate, in the case of an emergency, immediately to the nearest hospital. There's also a problem that since the observatory is in the Northern Cape, the state-run medical emergency folks aren't allowed to cross provincial boundaries. So they had to take, if there was an accident, they had to take them to a Northern Cape hospital. The nearest substantial one is 160 kilometers away over dirt road. Not what you want if you've got, for example, we had an accident 2 years ago where a Japanese astronomer fell off the raised floor of the Japanese telescope and broke his pelvis. You wouldn't want to be bouncing over dirt roads for 160 kilometers with a broken pelvis. Fortunately, we put him in a car and took him down to the much closer hospital in Worcester over paved roads. But now we'll have a proper ambulance to do that. Since it's our ambulance, we can drive it wherever we want and go to the most appropriate medical facility. The NRF has also made some donations to the local clinic in Sutherland that have upgraded its capacity, and the SAO has worked fixing some stuff. They've had some electrical problems and things due to poor workmanship, and we had our electrical staff come in and repair some stuff that had been long-standing issues. Let me close with a few of the coming attractions. Those of you who were here last year saw this same coming attraction. It's still a coming attraction, but now we have funds for a design study. So next month we're going to initiate a scientific survey of the astronomical community to define the science case for a 4-meter telescope, to be followed by a year-long engineering design study that will turn those scientific requirements into a full-up design document that will give us a high-fidelity estimate of the cost and time needed to produce a 4-meter telescope in Sutherland. There's not funding to build it yet. It's in the decadal plan, but the decadal plan is not funded. So we have funding only to carry out the study, but we hope that will generate enough momentum that at that point they can't say no. Actually, they're pretty good at saying no, but we can always hope. We also have funding to cooperate with NASA to build a Atlas telescope. There are several of these scattered around the world already. It's a network to detect near-Earth dangerous asteroids that could potentially impact the Earth, and it's designed to give enough warning to, ideally, if you have years of warning, to deflect the asteroid, or if you only have days worth of warning, at least you can provide the civil authorities with information about where and how big it's going to be, and they can take appropriate action. So one of those telescopes will be built in the next year or so at Sutherland and join this network that's patrolling the skies looking for dangerous objects. And we are working with our Japanese colleagues who already have an infrared imaging telescope. They want to build an infrared spectroscopic telescope at the site, somewhat bigger than the existing Japanese imaging telescope. And it's likely that we'll be able to find the funding from a bilateral program to build that telescope as well. So there's several new things coming on over the next year or two. And that's the summary from Sutherland. Thank you.
So my talk is also going to be slightly different, certainly different from Ted's, and maybe slightly different from what was previously announced, but I will focus on the relationship with Sutherland. And I do apologize if some of you have seen some of the slides before, because I've presented to the club on more than one occasion. So the facility that you showed that was incomplete, which I'm not going to talk about in detail, that is a collaboration with the German Space Agency, and that's a telescope that's going to be there for space debris tracking. So space junk, anything over 10 centimeters in size you can see from the ground with an optical telescope. So specifically for tracking stuff that people leave behind in space. Our facility, which is actually a container that we managed to sort of get from Cape Town Harbour, we bought it. So that's what it looks like. And it's in this location here, sort of. I don't know if it's precisely there, but it's approximately there. And this is going to be mainly for what we call mesospheric studies. So atmospheric studies below, between 20 kilometers altitude and 100 kilometers altitude. That's what the facilities are going to be there that we're installing. The Sprite campaign that we ran in December, January, February in this year, that was done from over here, but because we didn't have the container in its place. Future campaigns will be done from there. And yes, this is a pretty windy and pretty dusty location. So the first topic is to do with the sprites. This is some background. This is average lightning strikes per square kilometer per year. The Sprite phenomenon is powered by lightning strikes. And you'll see, of course, South Africa here is a lightning-rich area of the world. The tropics, of course, tend to be the most lightning-rich areas, and of course, where you've got mountain ranges and so on and so forth. But there's a lot of lightning, about 1.4 billion flashes a year, 40 to 50 times a second, most of it over the tropics and most of it over land. And it turns out that if you have a lightning strike, you get a charge displacement. That charge displacement is temporary, but it's sufficiently large that it sets up an electric field that lasts for around 1 to 10 milliseconds. So you've got your lightning strike down here below 10 kilometers altitude. That electric field projects up into the sky. And if you apply a high enough voltage to an insulator, air being an insulator, it will eventually conduct. So this is the breakdown voltage of air, and we're talking million to around 3 million volts per meter at ground level, and then it gets less and less and less as you go in altitude. Eventually these two curves cross. That is around 80, 90 kilometers altitude. You can then generate a gas discharge. This is sort of what an example looks like, and we call them transient luminous events. A very, very tiny fraction of lightning strikes will meet this criteria, be big enough to do the job, and therefore set off a gas discharge in the atmosphere. Okay, it's certainly less than 0.5% of all lightning strikes, so around 2 million a year, as opposed to the billions of lightning strikes that are out there. And this is basically what it looks like. This is a recording that was made from an aircraft in 1994. They start off around 90 to 100 kilometers, or red in color at the top, blue in color at the bottom, and this is the cloud illuminated by the lightning strike from below. And of course, it depends on the gas in the atmosphere. Mostly, in our case, it's nitrogen, so you're going to see the emission lines of nitrogen. If we were on a different planet, then we would see different emission lines. The dominant ones are blue, the bottom here, so 400 and something nanometers. Red at the top here, 640 nanometers and greater. And there's a strong UV emission which has been seen from space, but we don't know whether it's possible to see it from the ground because of ozone around 25 kilometers altitude would absorb it. That comes from University of Alaska. I believe it's the United States. I don't know the exact location, but it's from an aircraft in the United States, so flying above the clouds. Okay, I could find out. So briefly, the history. They were predicted by a guy called Wilson, British fellow who got the Nobel laureate in 1925, but they were first observed and recorded in 1989. This is an astounding fact because if about 0.5% of all lightning strikes produce Sprite emissions, and there are billions of lightning strikes, which have been around ever since the Earth existed, there's a lot of them. Everyone can see one. And I have seen them with the naked eye. You just have to look out for them. And they come in different forms. No time for all the details. Elves, this is the Sprite, blue jets, and so on and so forth. But they were all powered by lightning strikes. And the reason that they appear to be so rarely reported is, of course, you need a thunderstorm. And people tend to go inside when there's a thunderstorm. And their occurrence is sporadic, and people don't look up. You have to look up in order to have the thunderstorm. And of course, they're very bright, easily seen by the naked eye, but very brief. You have to not be blinking, otherwise you won't see it. So, this is the lightning map in the high lightning season in South Africa. You see lots of lightning, and this is Sutherland's location. And this is a field of view. This is roughly a 500 kilometer radius around Sutherland. The other location is Hartbeespoort Hoek, which is a station where we have a lot of telescopes for SANSA. That's for satellite tracking. So if we go here, which we did, you can see the storms to the north and the east of you. Also, you can see lightning over the ocean, which is much rarer. We haven't made an observation here yet, but we're looking for that opportunity. So December, January, February, we were out there, or more accurately, the student was out there. He had a camera. This is a very small camera, sort of thing you can just pop into your pocket. It's a night vision TV camera. And then this is just some geometry. If the Sprite occurs at a fixed starting altitude of 90 kilometers, the further away it goes, the curvature of the Earth means it will appear lower and lower in the sky. So you want the storm to be about 100 to 200 kilometers away so you can view over the storm. It's not raining on your head, but then you can see it. And if the storm is further and further away, then of course the Sprite appears to be lower and lower in the sky, and you see it lower and lower in the image. Now, so this was the first time we were successful, was on the 11th of January. There's Sutherland, there's the storm. This is what the clouds looked like. Later we were successful again on the 2nd of February. Again, there's the storm. There's Sutherland, and that's what the clouds looked like. And we use these satellite data from Meteosat to determine where to point the camera, because you have no idea where a Sprite may appear. And I'll show you the video clips now. So from the 11th of January, this is the first ever recording in South Africa, and you see some other examples. And they're all low in the image. The bottom of the image is actually the horizon. They're all low in the image because the Sprites are roughly, in this case, 550 kilometers away. The top of the Sprite being around 90 kilometers altitude. This one's obviously a bit closer. This is the 2nd of February. The storm was closer, but the geometry wasn't as good, and he was viewing through a window, which was a mistake. Students need to learn, so we won't be doing that again, but I'll show you the video clip. So this is a concatenation of all the video clips. Keep looking around here. There's one. There you can see one of the telescopes in the foreground. There was a Sprite there. There. In the first night of recording, this is the 11th of January 2016, we recorded 65 of them. You can see that the time is moving because the stars are moving in the picture. There's another one. There's another one. There's another one. Okay. They're all over the place, just that no one's ever noticed them. At any rate, we've recorded over 100 of them on 2 occasions now. And we will be back. December, January, February is the time to be there. And we've got our own container now with our little domes, and we can put cameras in there, and we don't have to worry about the dust and the rain and all those things. And we make these recordings. Okay. So we've got a lot of them. I won't run through the whole way. Right. So that's sort of where we're at with the Sprite project right now. In the future, we'll obviously use the observatory we're building. We now have 3 of these cameras, so I can use filters. Instead of just white light, I can put filters on so we can get the spectrum out. I have a camera with a bit more time resolution. This is going at 100 frames a second instead of 25 frames a second. Someone's agreed to lend us an expensive UV camera, and if the UV emission is very strong, it will penetrate the ozone layer and we will see it. And then we're going to put in our own lightning detector. This antenna here, which we've got here in our garden, will move up to Sutherland, and we will record the lightning strikes and the sprites, which have an electromagnetic emission which we can identify. And this is in collaboration with the UK. So that's coming up this summer. Then the next thing we're going to do is we have already installed an imager which we call an airglow imager. The atmosphere is never completely dark. The atmosphere between sort of 50 and 100 kilometers altitude has chemical reactions that go on all the time which produce photons. Now, this is an image from this International Space Station. There you see a bit of it. Of course, the planet below, and this is the atmosphere. And this line here is approximately 100 kilometers altitude. And the whole column of the atmosphere up to around 120 kilometers altitude produces light, which is easy enough to observe if you have the right equipment. This is a zoom up. Again, you can just see the color change. There's a sodium layer just over here, and there's an oxygen layer. The oxygen layer is sort of green. The sodium layer is sort of yellow in color. And so we can use those as tracers. If you can image the airglow, then you can see things happening in the atmosphere. So, of course, we've got the domes here, which Ted already showed. There's another one over here, which is different, which has this imager in it. It's basically a camera, wide field of view now, 180 degrees field of view, and it's sensitive enough with 2-minute exposures to look at the airglow emissions of the sky. Operation started in July 2016, and it's running right now, and you can see the data on the web. So this is data from the 22nd of September, so not long ago, a week ago, around 18 UT at night with a 2-minute exposure. The sodium emission, which is yellow in color, and you see the whole sky there, and you can see very clearly waves, these lines across the sky like that. Okay. This is around 90 kilometers altitude. If we switch to the green emission, and the filter wheel's got several filters on it, this is around 97, 100 kilometers altitude. Again, you can see waves. These waves are called atmospheric gravity waves. They're quite ubiquitous. They have a period of the order of 10 minutes to 30 minutes, and basically they're buoyancy waves where if you disturb the atmosphere through one process or another, gravity gives you the restoring force. And you can see these waves very beautifully. And they travel all the way from almost ground level up to several hundred kilometers altitude, transporting energy up or down depending on the initiation altitude. So we're just starting now to study atmospheric gravity waves using the Sutherland station. You can see gravity waves in many contexts, and you see them here all the time. This is just clouds. So we're talking around 100 kilometers altitude. Don't know where that came from. This happens to be in Antarctica, so this is a good segue to the next bit. But you see very beautifully, you see them in Hermanus as well, gravity waves. They can be brought on by many things, including just winds going over mountains or geomagnetic storms brought on by solar activity. And this is the start of our study. We're also planning to put into that container a Fabry-Perot interferometer. That instrument is also a passive optical instrument, and that will allow us to measure the winds in the atmosphere around 200 to 300 kilometers altitude, temperature and winds. We don't have that instrument yet, There's a small issue of 12 million rands to get my hands on one. But I do have one. I just don't have it here. And this relates to the trip that I did in January to South Pole. So this is a photograph. This is the geographic South Pole. That's where this pin is. It's literally the South Pole. Of course, the SANSA flag and me standing there. And you're up at an elevation of 3,000 meters. So in a collaboration that I have with the United States, I share one of these instruments. And one day we will get it here. But right now, it went to South Pole. So this is the Amundsen Scott South Pole Station. I'll show you a few nice pictures and then I'll show you the instrument. So this is the main entrance. This is what the station looks like from afar. If you really want to stay in a tent, you can, but I don't recommend it because the ambient temperature was about -30. It wasn't a bit chilly, and this is high summer. And you can see what the surrounding terrain looks like. It's pretty boring. It's flat and not much really going on there. Transport, they flew me in with other people on a US Hercules Air Force plane, a C-130, on skis. You can see it resting on its skis here. Okay, there's no runway. It just sets down onto the ice. And again, you can see it's pretty flat. In fact, the nearest living thing to South Pole Station is 500 kilometers away. And that's still not anywhere near the coast. It's just remarkable. On the way, just out of interest, we had to stop at McMurdo Station, which is on the coast, and that's Mount Erebus, the southernmost live volcano in the world. Of course, nothing actually happened, but it was puffing a bit of smoke. And this is a distance of about 10 kilometers to the volcano. This is flying to South Pole, and this is the Beardmore Glacier. You can see the glacier bit here and the beautiful mountains. And it's remarkable to think that 100 years on, from when Amundsen and Scott were struggling on foot over many weeks, like 6 weeks, to walk to the South Pole, we can hop on an aircraft, fly there, and be there within 3 hours. It's just incredible. So this is the instrument being installed. That's the frame of the instrument going into this observatory here. The main station is about a few hundred meters behind my back in the picture. And then this is the instrument. You can't see all of it. There are two instruments, one at South Pole, one at McMurdo. You see the bottom half of the instrument here. The whole thing stands 6 meters tall, and it goes into one of those domes. They're very, very conscious about heat loss at South Pole. Everything has to be closed. You can't open anything. So this is what the instrument sort of looks like, the bottom half. This is the bottom half of the instrument. And what can we do with this? These are examples now. The instrument has a field of view of 150 degrees, and what it measures is the Doppler shift of the atmosphere, so that means the velocity, and the Doppler broadening of the spectrum, which means the temperature. And in this case, we can get a wind field out. So with an exposure, this exposure I think is the order of 60 seconds. With an exposure of around 60 seconds in the whole field of view, which from edge to edge is about 1,000 kilometers across, we can work out what the winds are. In this particular case, we're operating at around 120 kilometers altitude. This is a picture of an aurora, and remarkably you can see the wind is blowing southward here. And when the aurora appears, you see the wind steers in the more eastward direction. When the aurora disappears again, the wind reverts back to the southward direction. And the energy required to do that, to rotate that body of air on these scales in 90 degrees in rotation, is enormous. So there's a huge amount of energy being deposited when there's an aurora on display. So this is just an example of the sort of thing we can do with this camera, with this device. And then, because it's an astronomy club, I did discover at South Pole that they have 3 telescopes down there, but they're all microwave. There are no optical telescopes whatsoever, and they work here in the 95, 150, and 220 gigahertz range. These two point vertically, and that one is fully steering. So that's the steering one here. I really don't know much about what they do. It's a 10-meter dish with a detector at 10 Kelvin. So they've got a cryogenic pump and all the things that are required to make that go. Mostly, there are vehicles, of course, at South Pole and other places in Antarctica, but in the base environments, mostly you're just walking around. And then finally, the temperature, minus 31 degrees, and this was on the 18th of January, so kind of midsummer is the temperature. I do know that, of course, I wasn't there in the winter, but they get minus 60 routinely in the winter, occasionally minus 80. And the other thing that's remarkable about going to a place like Antarctica, or in particular South Pole, you might be standing on top of 3/4 of the world's fresh water supply, but there's not enough water to drink. Okay, it's all frozen. So there were limits on how much water we could consume, and there were certainly very strict limits on how much washing and showering you could do. We were basically allowed to take 1 2-minute shower every 3 days, preferably less, okay, because the water simply isn't there. It takes a lot of energy to turn all that ice into water, and then when you're finished with it, it has to be disposed of. So they try to restrict the water usage. So those are the 3 things I wanted to touch on. The interferometer, which is coming to Sutherland, the Sprite observations, which we started and will continue, and the airglow observations, which we're going to do gravity wave studies with. Thank you very much.
It's one small step for man, one giant leap for mankind.